Yeah, we looked at that in the previous class. So what did we say it is? A simple reflex agent. Simple reflex agent. We say that it is one that does what? In the interest of time, it is one that acts upon what? It acts upon the current percept and does not consider the percept history, meaning that it acts reflexively upon what it knows now, the current state. Knows now the current state of the environment. So we gave an example of a what? Of a robotic janitor. Of a robotic janitor. So we said a simple reflex robotic janitor will always clean when there is dirt. So it will just be testing a condition. Is there dirt on the floor or not? If condition returns true, then it cleans. If it returns false, then it stays put, right? And then we talked about a model-based agent. Model-based agent is the one that has a prior knowledge of how the environment normally is, or how the world normally is. So it does not only test for the current state, but also for the model state. All right, how the world normally is, how the environment normally is, and therefore, based on the percepts it receives during that moment, it checks on how also the world normally evolves, all right, during a particular time. So we said, for if it is a robotic janitor, a model-based robotic janitor will first test if the floor has dirt, and then if the condition returns true, it will also check how the world or the environment normally is. If it is a veranda, how people normally pass through that veranda. All right, so it will know that people pass through the veranda, like from this time to this time, there are normally an average of 30 to 40 people that are passing through there, or there are, yeah, and this time to this time there are 100 people passing through there. So it knows how that world normally evolves, and therefore it is able to act according to how that world normally evolves. So if during that time, it is during the time when, uh, in its internal state. We talk about the current state and internal state. So the internal state, or the model state, is how the world normally is at a particular period of time. So if at a particular period of time the internal state shows that the number of the number of veranda users or passers by are 100, what it will do, it will do what? It will probably postpone the cleaning until the time when the people are 30 to 40. All right. So that's what it does, a model-based agent. And then a goal-based agent is one that has the capabilities of a simple reflex and a model-based, but in addition to that has a what? Has a goal. So it acts on a goal. So a goal-based robotic, janitor will have a goal that at every 10 minutes it's going to be cleaning. All right, at every 10 minutes it's going to be cleaning. During every 10 minutes it's going to be cleaning. So every 10 minutes it's going to be checking whether there is that or not. Then it returns true or false. Then it also checks the internal state of how that environment evolves. All right, the internal state. And also, then by checking the internal state and the current state through the capabilities of a simple reflex and a model based, then it does what? It completes a goal. And the goal is to do what? To ensure that every 10 minutes cleaning has been done, if there is that, every 10 minutes. Okay. And so today we want to look at number 4, utility based agents. Now, utility based agents, anytime that you are not able probably to hear my voice, you can say so, that because sometimes we experience those glitches in the system. So if you at some point you're not able to hear me, please you can say, so that I correct that. So utility based agents are goal based agents that not only perform actions to meet a goal, but also find the best suitable way to reach those goals, right? I will repeat, utility-based agents are goal-based agents that not only perform actions to reach a goal, but also determine the best possible way to perform or to reach that goal. Okay. So there are multiple possible alternatives, as you can see, I've highlighted there in the notes. There are multiple possible alternatives that can be reached, and an agent has to choose between those multiple possible alternatives in order to perform the best action. So the idea behind utility-based agents is to reach a goal by offering the best solution or through the best path. Now, if let's still go on and talk about the robotic agent. If a robotic agent is a goal-based agent, its work is basically to check the current state, the internal state, and to meet a goal. And the goal is to be cleaning every 10 minutes. That's a goal. But a utility-based robotic janitor, it will go further than meeting that goal. It will go into how that goal can be achieved best based on the current state and the internal state. For instance, it may want to be cleaning at exactly 10 minutes, like, in its looping, it has arrived to another cycle of 10 minutes. But during that cycle of 10 minutes, because you remember it still has the capabilities of a model-based agent, the internal state informs it that during this time, there are many people that are passing through the veranda. So how does it clean? Yet it has to reach the goal. 10 minutes. So what will it do? It will check for the areas that people are not really stepping on. Yeah. And it will go as it meanders through people, and cleans those particular areas that people are not stepping on. And then, it goes and, cleans at a certain point, like it can clean the right path, right? It can clean the right path so that people can pass through the left path. And then it now cleans the left path so that people can pass through the right path. Okay, so it performs an action. It performs an action that meets a particular goal, but that action is the best possible action. It's not just a random action that meets the goal. It is the best possible action. So utility based is like this. For instance, you're going to Nairobi. You're driving to Nairobi. So you're driving to Nairobi town, but there are different routes that you can use. Let's say you are coming from the interior parts. There are different routes that you can use, but there is the one which is the best based on some certain conditions. All right. So here, the best possible action is also influenced by some certain conditions. For instance, economic performance, like a robotic janitor must ensure that it uses the best actions that least impact on its power consumption, because it is a robot, meaning that it has power, it has battery, yeah, it has power storage, right? So the one that least impacts on its power usage, yeah. The one that least impacts on its resources, because we are assuming here that it is using what? In the previous class, we said that that particular agent can have a brush, it can have, sanitary soaps for washing the floor, right? Such things. So the one that least impacts on its resource usage, because it might pick on a particular action and find that it cleans a lot. It cleans, and then people are still passing, people are still stepping. It cleans again, people are still passing and stepping. It has to clean again. So it negatively impacts on the resources that it uses. So the best possible action is normally arrived at by looking at how, number one, how the action impacts on the agent itself, and how the action impacts on the environment itself. So it cannot go around cleaning and hitting people on the way. That robotic agent, it cannot do that. Also, it cannot go around cleaning and use a lot of sanitary, soap, or those soap for cleaning the floors, the hygiene, for cleaning the floors, yeah. Or it doesn't take an action that highly impacts on its power usage. All right, so that's why I've highlighted in the notes. As you can see, it has to pick the best possible action, and that action must be determined by those kinds of factors. So as I was saying, as you are traveling to Nairobi from the interior parts, you have to check for the best possible way of achieving a goal. For instance, your goal is to reach Nairobi. You are getting from your area, from your source point at 9:15 or 10 a.m. And so your goal is to reach Nairobi at noon, based on where you are. At noon, let's say noon. But then there are different things that you have to pick on the way. There are different things that you have to pick on the way and different things that you have to do during your journey, right? So you're not just traveling straight without stopping. So you'll stop over at some point to pick some things, probably to meet a person or to pick up, some shopping or things like that. Yeah. So as you do that, you will have to determine the best possible action that you do. Will you travel? Which path are you going to use? Which road are you going to use? How many number of stops are you going to consider on your way? Yeah. And also how are you going to, how much speed are you going to accelerate on your way, even as you drive down to Nairobi? So basically, you are taking the best possible actions that will meet that goal. The goal is to reach at 12 noon, right? So you take the best possible actions that will reach that goal, and that is exactly how utility-based agents work. So as you can see, this is the structure. This is the structure of a utility-based agent. So first of all, it checks for the current state, what the world is like now. Yeah, so here we are talking about a robotic agent, like a robotic janitor. So what the world is like now. For instance, is the floor clean or is the floor dirty? That is the current state, what the world is like now. Then this current state is also influenced by other things like the internal state. All right, the internal state is the state of the model, right? Like how the world evolves, how the corridor, what number of people pass through a corridor at a given time. All right, there are those algorithms to determine those number of populations. So the internal state, the model, all right, and also how the world evolves and what my actions do. In other words, when the floor is dirty and when the corridor has 100 people, 50 to 100 people passing through the corridor at a given time, what do I normally do during that scenario? Then when all that has been determined, floor is dirty, there are 100 people right now, and there are possible set of actions. So what my actions do is a possible set of actions, not just one action. Possible set of actions that can be considered based on this state and based on the model. Okay. And so floor is dirty. There are 50 to 100 people at this particular point. There are 100 options of actions that I can do. So it puts all these things to a test, what it will be like if I do action A. All right, so it will test for all these actions. So based on this state and based on the model, it will test what will be the impact of each of these actions. So there are, let's say, 100 options that it can pick from. It will test each option. So if I go around cleaning, what will be like if I do action A, if I go around cleaning at that point? All right, what will it be? How will it be? Right, so it will test for each action and the impact it has, number one, on itself, and number two, on its environment. Okay, and then there is something called utility. Utility is basically a measure of how satisfied the the agent is. Okay, look at this. It makes the utility makes the agent different by providing a measure of success at a given state. So every time it performs an action, it measures how satisfied it is. But satisfaction is basically a state, a thing that we normally talk about when we are talking about living organisms like human beings and animals. Yeah, it is living organisms that can have a feeling or sense of satisfaction, right? But for how does an agent reach a sense of satisfaction? It tests what we call performance measure. Performance measure. Performance measure is a ratio of how successful an action was, and how successful an action was, and if that action had the least negative impact on the environment and the least negative impact on the agent itself. That is the performance measure, right? So performance measure is a ratio, right? So how happy will I be in such a state? So that is a performance measure. If I perform this action, how will I be satisfied? Will I be satisfied? In other words, will that action lead to me lead to the at least the least negative impact to the environment and the least negative impact to me as an agent. So that is what we call satisfaction rate. It's called the best performance measure. Then when it picks on one, so when it determines that there is one action, when tested against the performance measure, what we call the utility, it returns something like at least 80% or 90% performance measure. Then it picks on that action as the resultant action. The resultant action is the last or the final action it will now take. Yeah. So if it is a robotic motor, then now it can say that the best action among all the actions that I have tested, the best action that has the highest performance measure is where at this point floor is dirty, and at this point there are 50 to 100 people passing through the floor, on the floor. Then the best action will be to set a barrier on one side of the veranda. If it's the left side or the right side, on one side of the veranda, clean it. Remember, the goal is to do what? To clean before 10 minutes elapses. All right. So within those 10 minutes, you should set a barrier, clean that area that it has the barrier blocks, cleans that area. Then it removes the barrier, sets the barrier on the other side of the veranda, the left side. It cleans that area and releases people to pass through here. So within 10 minutes, it has ensured that the floor is clean, and yet it has not gone around cleaning and meandering and hitting people. And also, it has not, the goal has been reached. 10 minutes has not elapsed without the floor being clean. So basically, can you see how that works? So utility-based agents, they always measure their success and how satisfied they are. And how satisfied they are is determined by what? The performance measure. And the performance measure is the success rate of actions that least negatively impact the environment and least negatively impact the agent itself. All right. So when it comes up with the actions, then of course it can perform the action through actuators to the environment. And the actuators here is what? Is the brush, or in the previous class you said it can also be a vacuum cleaner. But if it's a more manual robotic agent, it can be a brush and soaps, right? Those can be the actuators. It releases soaps and uses its brush to go around and water. Yeah. Okay. So that's how utility-based agents work, by not only meeting the goal, but also identifying the best possible action, the best action that will meet that goal, not just meeting the goal. All right. Learning agents. Now here we are going to, of course, there is a topic ahead that is called machine learning. Okay, but we are going to discuss it more there. But basically, the idea behind learning agent is an agent which can learn from its past experiences. Yeah, it can learn. It has learning capabilities. It can learn from its past experiences. Therefore, It first starts to act with basic knowledge, and then it is able to act and adapt automatically through learning as it achieves things in its environment. A learning agent has mainly 4 components. There is a learning element. A learning element is basically an algorithm that improves itself, that self-improves. All right, it is a code that self-improves. It's called a learning element. It is responsible for making improvements by learning from environment. So it is a self-improving algorithm, right? It auto updates every time it meets new experiences or new challenges. This algorithm auto updates so that it becomes part, it imprints into its memory so that the next time it meets related challenges, it knows those challenges. Okay, it auto updates itself. Then it has a critique component. A critique component is an evaluator, all right, or an analyzer. A critique component is an evaluator. So this evaluator, it takes feedback from critique, which describes that, it describes how well the agent is doing with respect to a fixed performance measure. So a critique, again, as we said in the utility-based agent, it does what? It checks, it tests for the performance measure. Here, it's not called a utility. It's called a critique. All right. A critique is basically a what? An evaluator or an analyzer. Its work is basically to test every action that has been taken against other conditions to see if it is the best possible action. So some actions can be discarded, some actions can be stored up for future use, right? So a critique is an evaluator. Just like you, a human being, you go through your head and you ask yourself questions about what's wrong and what's right about the environment you are in. So a critique is one as that asks some particular conditional questions, all right, in order to perform conditional tests, and therefore it comes up with a performance measure. And then it picks on the actions that have the greatest performance measure, like those that are 50% equal to and greater than 50%, right? It picks those ones and stores them for future use. Then performance element, it is responsible for selecting external action. So performance element is what we call an action. It is an action, it is an action generator, okay? An action generator, performance element. So remember the critique component tests, evaluates, it analyzes different actions and their performance measure, and then it picks probably the ones that have 50 equal to or greater than 50% performance measure. Those ones can be considered to be optimal, to have an optimal performance measure. Therefore, they can be used for future actions if some certain problems are faced during the in the environment. So during when the agent has to pick on an action, then it is the performance element component that selects an action, all right, that selects an action that the agent will perform. It's called the performance element. So it will select one of them. It will select one of the many that were picked by the critique component, okay? Then the problem generator is responsible for suggesting actions that will lead to new and informative experiences. So when performance element selects actions that are already known, problem generator suggests actions, new actions that can lead to new and informative experiences. Okay, so performance element in a pick from the actions that are already there. But problem generator, it's the one that suggests other possible actions that have not been critiqued. Remember, these actions now for the problem generator have not been critiqued. They don't exist. All right. But based on some certain algorithms, some certain mathematics on how this particular action will influence the environment or will influence on the agent, it can suggest, this problem generator can suggest to the agent new actions that have not been critiqued yet, but new actions that can be experienced or that can be tried out. And then you see this problem generator is actually the main component in a learning agent that helps the agent to come up with new ways of doing new things. Otherwise, it will just be a utility-based agent where it just measures its utility, the performance measure, and therefore it keeps iterating between actions that it already knows. Okay, so this performance element works like the utility. All right, it iterates between actions that it already knows. So it has 100 possible actions. So it just picks one of the 100. It can pick action 98, action 53, yeah, and then actuators just perform that action. But problem generator is one that does what? It you know, it suggests new actions that are not in the performance elements. It suggests new actions, and therefore these new actions, when they are done, then which part of the learning agent will analyze if that action was good? It is the critique, right? So with every new action, the agent will critique. All right, it will evaluate. All right, so these are I think now you're understanding how this thing works. Okay, so for every new action that has been performed, an action that was not there in the performance element, for every new action that has been suggested and done, then the agent will go back and critique it, right? Then if it had a performance measure of 40%, then it will be discarded, meaning that it will not be in the performance element chart. All right, so I can call it a performance element chart, a chart to show all the possible actions that have an optimal what? An optimal performance measure, 50 to 100%. So if ili try out, kama ili try out a new action that is not in the performance element chart, then by critiquing that action has a performance measure of 40%, then it discards that action. So it is not recorded in the performance element chart for future use. But if it is 50% and more, then it is recorded. The performance element is it's recorded in the performance element chart. So so it will be one of the actions there. It will be one of now a new action among the very many other actions that it can do. All right. So for instance, let's talk about a robotic motor. Not a robotic motor, but a robotic janitor. A robotic janitor may have a number of actions that it can perform, like setting barriers so that it can clean, yeah, or going through the places that people are not stepping on and cleaning those areas, or waiting for people to reduce, right? Waiting for people to reduce, or setting a barrier all through so that it can clean fast within 2 minutes and then allowing people to pass. Right? So instead of dividing the area, blocking the whole area, and then it cleans the veranda, people are blocked, they cannot pass, and then it does that through, in 2 minutes. So it has to have it clean within 10 minutes, but it ensures it's clean within 2 minutes so that the place is dry and people can pass. All right. So those are some of the things that it can do, right? Some of the things that it can do, but then it keeps on learning, meaning that it is able to consider new actions for new experiences. So learning agents are mostly they end up sometimes being or close to super intelligent agents. Why? Because they are able to learn from their experiences and self-improve. Why? Because they have this critique element. All right. So if I ask you what are the four components of a learning agent, these are the ones. Learning element. A learning element we've said is what? It's an algorithm that is able to auto-update and adapt to new experiences. So it changes. It is like a code that self-improves without being recorded by a programmer. A code that is able to self-improve. Learning element. Then critique is an evaluator, and these is made up of conditional statements and algebraic expressions. conditional statements, and algebraic expressions. If x is equals to this and z is equals to this, then bx plus m will be what? Or bx times m minus 2 will be what? So that's a critique component, an evaluator to check the performance measure of an action. Then the performance element, it's one that is responsible for generating an action. So we've said that the critique, because it's a mathematical component, it's an evaluator. This mathematical component called critique, after evaluating all the actions, then it does what? It stores up all the actions that have at least an optimal or high performance measure. All right. Then the performance element is now when a problem has been experienced in the environment. A problem is not really, it's not a problem, is just something that has to be done. We call it a problem, all right? A challenge, okay? Like a solution that has to be, that has to be a thing that requires a solution. It can be cleaning, it can be driving for a car, it can be playing music if it is an intelligent, if it is an intelligent media player system. That's a problem, right? So performance element just generates an action from the set of actions that have already been critiqued and found to have an optimal and high performance measure. So ni kama wewe ukitaka kufanya kitu, there are things that happen in your brain, and consciously or unconsciously there are things you normally evaluate. So before you do an action, normally and mostly you look at how that action, if you normally your brain takes you back to the last time you did that action, how it affected you, how it affected other people, how it affected an environment, what did it cause, did it give you satisfaction, right? And then if it never gave you satisfaction, that means you will discard it. So that is why the critique is very important. Its work is to it's basically a mathematical evaluator to test every action that has ever been performed and only pick on those ones that are 50 to 100%. Then the performance element is one that will pick one when that problem has been faced. So if it has 120 possible actions that have 50 to 100 that had been critiqued, measured, computed, and have been selected to have 50 to 100 performance measure, then one of them will be picked, not all, one of them will be picked. Then that one will also be critiqued again. So in that situation, if that one we had a 70% performance measure and it has been picked by the performance element, after being performed, when critiqued again, it can be found that now its performance measure has lowered to 50, right? Because probably in that situation, it was not really the best. It was one of them, but it was not really the best. I think you understand what I'm talking about. Then problem generator is one that enables it to learn new experiences by suggesting to it new actions. So this is I think I can say that this is the most important part of learning, because you can't learn without trying new actions. Even in real life, you can't learn without trying out new things. So the problem generator is it is the creative component of a learning agent. It suggests to the agent actions that it can do, actions that have not yet been critiqued, but they are possible actions it can do based on the problem in the environment. And then when it performs that action, it is critiqued, right? And then if that new action has a best performance measure, then it is included in the performance element chart to be considered in future. So look at that structure. I feel I've talked a lot. So there is this is the environment. So the percepts goes through the sensors of the system. Then when that input has been received, it has to critique the different actions it can take. Then the learning element does what? For making improvements, it auto updates. After critiquing, it auto updates. Then it can suggest new actions. And then it's this performance element that now suggests, generates an action, the final action. So if it suggests an action, it passes through the performance element so that that action can be passed to the effectors. So if through this learning element there are things that have been updated, functionalities that have been updated, and those updates have to be also passed to the performance element. That's why you can see these arrow changes. Okay, and then there is this knowledge. The performance element also has a knowledge of different actions. So this knowledge every time has to be passed again to the learning element. So the learning element is a back and forth component which updates changes to the performance element and also receives new knowledge from the performance element. So it keeps on auto updating and changing itself. So this is the part that grows. Okay, this is the part that grows, right? The part that grows. So learning element can influence this. The learning element can influence new actions that have never been critiqued, and then these new actions are passed to the performance element, and then the performance element passes the final action or the resultant action to the effectors, and then the effectors can perform an action to the environment, right? Any question up to that point before I go to agent environments? Any questions to that point? All right, Colin. Juma, Vivian, Jesse, Dennis, Edmond, Bashir, Jefferson. All right. I need a break to take water or something. I've talked a lot. So let's have a thank you, Mulongo Bashir. So let's have a 10-minute break. Yeah. I mean nikunywe maji, be fine. So that we continue. So you can have a 10-minute break to yourself. We resume at 9:50 so that we now do the last part of our class. Okay. So think about those things we've just learned. So give ourselves 10 minutes break. You reminisce on those things that we've learned. You chew on them. Then we at 9:50 we resume. All right. Resume the recording. So we are back. I hope that everyone can hear me and see me clearly. Let me share the screen so that now we can move on to our next item. And I hope as you are there, you're actually very keen as we are going on with the class. We can be in class and you're actually really not there. You're there, but you're not there. You're just listening, but you're doing your own things, meaning that you're not really there. Right? Let me refresh my page so that I'm able to share my screen. I'm not able to share my screen. Let me refresh it so that I may bring back that feature. So as I was saying, I hope that you are really in class. You know, you can be there, you're listening, you're online, you're listening, but you're not really listening. You're just there doing your own thing. So I hope that you're actually listening and that you are also taking notes because the idea of having a class, after all, you will have the notes in the system, but the idea of having a you know a class is so that you can learn things that probably the notes will not be able to explain. So the class helps you to learn things that you may not be able to well understand through your notes. That's the idea of the class. So ensure that you're also writing down some few things even as we are learning. Okay. So I want us to do this, if possible, if we're able to finish it. I want us to do agent environments, different kinds of agent environments. So begin by defining an environment. An environment is everything in the world which surrounds the agent, but is not part of the agent itself. An environment is everything that surrounds the agent, but is not part of the agent. Like for instance, if we are talking about a self-driving car, the environment for the agent is what? Things is composed of things like the road signs, pedestrians, yeah, things like that. But it does not consist of things like infrared sensor, accelerator, wheels, steering. Why? Because those are parts of an agent. Those are not environment of an agent. They are parts of an agent. So an environment is everything that surrounds the agent, but is not part of the agent. Okay. So an environment can also be described as a situation in which an agent is present. Where an agent is can also be called the environment. So it is also where the agent lives, operates, or functions in, and provides the agent with something to sense and act upon. So we are also saying that an environment is where an agent lives, where an agent operates, and also that which gives the agent inputs, all right, from where the agent receives its inputs is also called an environment. So by definition, generally, you can say that an environment is what surrounds an agent, what gives inputs or percepts to an agent, where an agent operates or lives in. Okay, that is what can be called an environment. An environment, features of an environment, as per Roussel and Novig, an environment can have various features from the point of view of an agent. So according to Roussel and Novig, there are 8 different ways we can classify agent environments. According to Roussel and Novig, there are 8 different ways that you can classify an agent environment, and each of these 8 different ways have particular features that we are going to look at. Right, so let's go then to each. So we have fully observable versus partially observable environment, static versus dynamic environment. So of course, these are way of comparing, yeah. That's why they come in pairs. Discrete versus continuous environment, deterministic versus stochastic, single agent versus multi-agent environment, episodic versus sequential, known versus unknown, accessible versus inaccessible. So these are the 8 different ways of perceiving agent environments or thinking, conceptualizing agent environments. According to Roussel and Novik, there are different other ways of classifying agent environments, but these 8 different ways is the most acceptable way because they fully describe different agent environments. Roussel and Novik did a good job to come up with this. They do a better job in classifying and understanding these environments. Let's start with the first one. Fully observable versus partially observable environment. All right. So if an agent sensor can sense or access the complete state of an environment at each point of time, then it is a fully observable environment. But if an agent sensor can only sense or access a partial state of an environment at each point of time, is called a partially observable environment, right? So if an agent, for instance, if let's say a robotic janitor is at a certain corridor and it is able to see the whole corridor at all angles, then we can say that environment is what? Someone? That environment is it is able to see the environment, the corridor. The corridor is supposed to clean. It's able to see the whole corridor at every angle. That environment is like what? Is it a fully observable or a partially observable? It is a fully observable environment. That is true. That is true. Fully observable environment. Good. And if it is not able to access or sense or access the complete state of an environment, it's only able to sense or access the environment partially, it's called a partially observable environment, right? Partially observable environment. All right, so a fully observable environment is easy as there is no need to maintain the internal state to keep track history of the world. Yeah, so we don't need to keep a model of how everything is because it can see everything at every particular point in time. It can see everything during its operation. So that's why we are saying it does not need to maintain the internal state. It does not need to maintain how the world looks like. Why? Because it already knows how it looks like. It can see. All right? It can see. So it doesn't need a model of the world. Yeah? It doesn't need a model of the world. But there are things like, for instance, let's talk about a self-driving car. You know, a self-driving car will be working, of course, from a road environment where most of the things cannot be determined at at face level. There are things that change during in an environment of a self-driving car. The self-driving car cannot know if there will be pedestrians at some point. It will not know if there is a what? If there is a, it will not know if there are normally bumps at some point. It will not know if there are normally road signs after 1 kilometer because probably it passes through different routes. So it will not know there are normally road signs. In other words, it cannot determine everything where it is at a particular point. So it has to have a knowledge of how things are in its environment. So you'll have to code it with information about road signs, with information about bumps, with information about how to maneuver through pedestrians when it meets pedestrians, so that it may not knock them. So it may also have to have knowledge about road signs, I have said, and other things that it cannot know at face value because it cannot see the whole road to the destination. All right, so it has to have a model of how things are, things that it can expect to experience. All right, so that's a partially observable environment for a self-driving car. But for if it is a robotic janitor and it is for cleaning, it's supposed to clean a certain corridor basically. Or I think you can actually go to YouTube and you will see actually people hate washing toilets, right? People hate washing toilets. It's not a job that people love. Even in your own house, you don't love washing your own toilet, if I'm honest, right? Yeah. So it's a job that people love. So you will find that China, they have developed some kind of robotic, cleaners, robotic janitors that specifically are for toilets. They wash the toilet when somebody moves out. They can sense that somebody has moved out. and they go in and they wash everything. They wash everything so that it can be clean before the next person goes in. So basically, those are what those are that kind of an agent is a it will be working in a fully observable environment. It knows what to expect, everything. It knows everything. It knows the walls. It knows how many number of toilets there are inside that room, the toilet room. It knows how many number of rooms there are in there. It knows then sinks. It knows how the floor is made up. It knows how the sinks are. It knows everything in its environment. So it just goes ahead and goes and does what it does, having a full knowledge. So that's a fully observable environment. But a partially observable environment is one that it cannot know everything it needs to expect at face value. So it has to have a model, and therefore it has to be at least a utility-based goal, a utility-based agent, or yeah, a utility-based agent, or a model-based agent, a model or a utility or a goal. All right, then. So an agent with no sensors in all environments, then such an environment is called unobservable, an environment that cannot be fully known at face value. Then number 2, deterministic versus stochastic. If an agent's current state is the input, like is floor dirty, yes, that is the current state. If an agent's current state and selected action is clean, let's say, can completely determine the next state of the environment, then such environment is called a deterministic environment. Okay. Now, this is it. For instance, let's say sometimes you are playing a game. All right, you're playing a game. Normally, if you are playing a game like it's a game for riding a car or riding a motorbike, those kinds of games. You ladies, apart from Candy Crush, which other game do you know? Yeah, I know you know Candy Crush, but anyway, but even Candy Crush, all these games that you play, normally there's a way those games work. When you give that game input, when you give it input, because now you are part of its environment. When you give it input, then it performs a certain action. All right. Let's say it is Candy Crush. You move those fruits, then other fruits come in, and when those fruits come in, they are arranged in another manner which they were not arranged before you gave it inputs and before it performed an action. All right. I think all of you have interacted with Candy Crush at some point, but of course, Candy Crush is more feminine, I believe. If you find a man playing Candy Crush, that's somebody the problem, I think. Yeah. Men play other games like riding of cars and riding of bikes, right? Basically, what I'm saying is deterministic environment is one where when it receives an input and it performs an action, the state of the environment changes. In other words, the state of the environment changes based on the current state and the actions it has performed. So ukicheza, if you're playing the motor racing kind of game, when you are riding it, when you give it inputs like speeds, inputs like turning and such things, those kinds of inputs, then the game will be performing certain actions like moving that thing or bringing other cars or bringing other bikes in front of you so that you can compete with them. All right. In other words, every action that agent performs, the agent being the game, if it's an intelligent agent, yeah. If every action that it performs, it changes the state of the environment. All right. That's why you'll realize if you're not racing, there are things that will not happen. There are, for instance, you will not see some certain cities. If you are racing across cities, you will not see some certain cities. You will not see other cars that are passing you. Yeah, things like that. Why? Because the next state of the environment is determined and influenced directly by the current state and the actions it performs. In other words, the state keeps on changing. It's determined. That's why it's called deterministic. It is determined by the actions it performs. Therefore, if it is Candy Crush, if you move those fruits, if you do not move those fruits, the next state will not change. It will remain as is. But if you move those fruits, that's an action you performed, all right? The current state has changed. So the next state is directly influenced by the action you perform, right? The action you perform. That's why we are saying an agent's current state and selected action can completely determine the next state of the environment. All right. Then therefore that such an environment is called a deterministic. It is determined from the current state, in other words, the inputs it receives and the selected action. Or if we go back to the issue of the robotic janitor, if the current state is dirty, floor dirty, and the selected action is clean, then it performs action. So now the state has changed what? Clean, right? So the state has changed due to what? An action that has been performed because of a previous state and an action that has been performed, right? So where the next state changes based on the current state and the selected action is called a deterministic. But then a stochastic environment is random in nature and cannot be determined completely by an agent, meaning that even after performing that action, the next state cannot be completely determined because there are other things that influence what? There are other things that influence the state. There are other things that influence the state, right? So in a deterministic or fully observable environment, agent does not need to worry about uncertainty. Why? Because in a fully observable environment, it knows everything in its environment and it has a list of expectations. And then in a deterministic environment, it also knows how the next state will be if a particular action is performed. But in a stochastic environment, there are worries about uncertainties. All right. So stochastic environment, we normally build, let me go back here. We normally build model-based agents. We normally build model-based agents for stochastic environments. Why? Because model, at least it keeps a record of how the world normally is, right? As we looked in this structure, how the world evolves. So, meaning that it can handle what? Uncertainty. All right? Uncertainties. It can handle uncertainties. Let me go back here. So that is deterministic versus stochastic. Deterministic is one that the state completely changes to a known state when an action has been performed. But a stochastic is that when a current state plus an action is performed on a current state, then the next state is not known. It is uncertain. It is not known. Yeah. So it has then to be a what? A model based, meaning that a simple reflex agent cannot work in a stochastic environment. It can only be worked. A stochastic environment can only a model based and others. Model based, goal based, utility, and learning agents can work in stochastic environments. All right. Episodic versus sequential. Episodic versus sequential environment. An episodic environment, there is a series of one-shot actions and only the current percept is required. And only the current percept is required for the action. So of course, when you read this particular phrase here, what comes to mind is simple reflex agents, because simple reflex agents only work on one particular input per time. It works on only one particular input and it doesn't have to read from the percept history. So only the current percept is required for the action. It is not influenced by other percepts in the history. Yeah. So an episodic environment is one that requires one-shot actions. One-shot actions ni kama, let's talk about Eliza, the Eliza app. So you ask it something and it gives you an answer. You ask it something, it gives you an answer. Or even the chatbots. You ask it something, it gives you an answer. So basically, it gives you an answer not based on what you have been asking it before, but what you have asked it now. So it doesn't read from its percept history. It only perceives the current percept and responds to it. Okay, so that is what you call an episodic environment. It's called a one-shot action, meaning it performs one thing for one input, one action, one input. All right. So you ask it if it's a chatbot for an e-commerce site, you just ask it about smart TVs, right? Smart TVs UHD, and then it tells you there are no smart TVs UHD for Samsung or TCL, something like that. So basically, it performs one-shot actions based on one particular input you've given it. Episodic, meaning that it doesn't give action from a percept history, but the current percept. I hope you understand. And then a sequential environment, an agent requires a memory. Now, this is what is key. An agent requires a memory of past actions to determine the next best actions. So therefore, sequential environment is where an agent must work from a history of percepts. It does not only work from one particular input. So you give it an input, but the answer it gives you, it's not from this particular one input. It's from a range of other inputs, similar inputs that you gave it or somebody else gave it. All right. So, and in an episodic environment, it only works, it's an environment where the agent works on only one input and gives one action. That's why it's called a one-shot action. One input, one action. And then sequential environment, it works from a percept history. All right. It does not just get an action from a one percept, but numerous percepts in its history, in its percept history. Then single agent versus multi-agent. All right, if only one agent, if only one agent is involved in an environment and operating by itself, then such an environment is called single agent environment. However, if multiple agents are operating in an environment, then such an environment is called a multi-agent environment. So if we have a one robotic janitor on a corridor, that corridor, if it's a corridor of 700 meters, if there is only one robotic janitor, there are normally these, of course, organizations and hospitals and, of course, organizations, where there are normally corridors, very long corridors that even range from 700 meters to 1 km, depending on how long the building is. So if there is one robotic janitor working on that particular one corridor, then we can say that that environment is what? A single agent environment. There is no other robotic janitor within that environment. But if within that particular one corridor, there are two or more robotic janitors, so we can say that's a multi-agent environment. Or if there is only one self-driving car in one particular road route, then we can say that that road is a single agent environment. Why? Because there is only one agent. There is only one self-driving car. But if there are different self-driving cars, then it's a multi-agent. All right. Okay. So that's what we are talking about. Then, right. Then let's move on to static versus dynamic. Static versus dynamic. Just a minute. All right, static versus dynamic. If the environment can change itself while an agent is deliberating, then such environment is called a dynamic environment. But if an environment does not change itself when the agent is thinking on actions, then it is called a static environment. All right, this is the explanation. A static environment is one that does not change when the agent is deciding what to do. For instance, on a corridor, if the corridor is dirty, if the floor is dirty, then it is deliberating on actions to do. And actions to do then is block one area and then clean. All right. But there is no way that floor can change from dirty to clean as that agent is deliberating on what to do. It's a static environment. Why? Because it doesn't change when that agent is thinking or processing actions that it needs to perform. But if the environment is already changing, it's called a dynamic environment, right? Because at the point that is the agent is thinking about actions to perform, the environment is already changing state, meaning that it has to have a very, very fast, high-speed processor so that to accommodate the changes in the environment. Yeah? So static environments are easy to deal with because an agent does not need to continue looking at the world while deciding for an action, right? So if floor dirty, then it doesn't have to continue to look at the floor. It just goes back and processes its actions. But in a dynamic environment, then it has to keep looking at the world while still processing actions. Why? Because the world is changing. All right, the world is changing. Let's look at this example. Taxi driving is an example of dynamic environment. Yeah. Why? Why is the taxi driving a dynamic environment? Because every time it keeps, for instance, if it stops to, if a self-driving car, self-driving taxi has stopped to pick a passenger, all right, that passenger can decide what, or they are not going, right? They can decide they are not going. They have to wait for somebody else, right? That environment can change. It's so dynamic. Or at that time that it has stopped, when it wants to move, there is another car that has come to pick passengers or to drop passengers. So how should it deal with all those changes in the environment? Or when it wants to take off, the highway is busy. So it has to wait until the highway is a little not busy and then join the highway. So in other words, there are very, very many things changing within the environment of the agent, such that at every time it is performing a particular action, it is also looking at the world around it, because the world around it is always changing. But when you talk about a crossword puzzle is a static environment, right? Because it doesn't change. When you put a word and a letter, it doesn't change how that crossword puzzle needs to behave, right? We just group those words unazipanga venye ziko. Again, tulikuwa tumeangalia the example of a robotic janitor. If the floor is dirty, then it is dirty. It doesn't have to go keep looking at the flow if it is dirty or clean, because it has already determined it's dirty. So it has to resolve on actions. But if it's a car, a self-driving car, it is working on a dynamic environment, because the road keeps on changing. Pedestrians change their decisions. Potential passengers can change their decisions on whether boarding, and passengers on board can change their decisions on it where they are highlighting. They can say, okay, let's just move on, nenda kushukia huko mbele, right? And then therefore, that is an environment that is always changing. You don't know what to expect, right? So deterministic, dynamic environment also is like stochastic environments, okay? Because there is what? Uncertainty, okay? There is uncertainty. Okay, discrete versus continuous environment. Discrete versus continuous environment. A discrete environment is where there are finite number of percepts and actions that can be performed within it. In other words, there are a number of inputs that the agent already knows it can get. Those inputs can be in form of sound, heat, that can be in form of, visual sensors, visual sensory percepts. They have a finite number of percepts. So, like a robotic janitor, it will in its deterministic environment, where it already knows what to expect. It can also know how many number of percepts it will receive, and the percepts are just two, right? Clean or dirty, floor clean or floor dirty. Those are the only percepts it can receive, all right? And then it has a set of actions that are numbered. A set of actions that are numbered. that can be performed based on the percepts. So for a robotic janitor, there are a set of actions it already knows. It will just be picking from them, like block an area, unblock an area, clean an area, move to another area, block an area, and block an area. So in other words, it has a particular set of actions that it already knows. It is just waiting for the what we call the permissible situation. The permissible situation is the one which will allow it to pick one of the actions, right? So it already knows what to do, and the number of things it can do. It already has a number of things it can do. It's just waiting for a permissible situation, whether floor clean or floor dirty, something like that. So a discrete environment is one where there is a finite number of percepts, a number of inputs it can receive, and also it has a number of actions that it can perform. It just picks one. So if we pick another example, like a chess game comes under discrete environment. Why? Because there is a finite number of moves that can be performed. So there are different number of moves that can be performed. Why? Because of probability. The probability gives what? A number of moves that can be performed if it's a chess game. Yeah. But a self-driving car works on a continuous environment. A continuous environment is one where there are no finite number of percepts. In other words, those number of percepts cannot be counted. They are many. Why? A dynamic environment is also a continuous environment. Why? A dynamic environment keeps on changing. So that means that the percepts from the environment will keep on changing, even as the world keeps on changing. But also a continuous environment, there are infinite number of percepts, continuous, infinite number of percepts. So in a dynamic environment, there will be dynamic environment is also a continuous environment because of the change. All right. So a self-driving car is an example of not a self-driving car, a road for a self-driving car. I'm sorry for this. A road for a self-driving car is an example of a continuous environment. Okay. A road, not self-driving car. Self-driving car is a what? Is an agent. So a road for a self-driving car is an example of a continuous environment. Why? Because there are numerous number of percepts that cannot be counted. It can be the cry of a baby in a car. It can be the sound of hoots. It can be the sound of people talking by the roadway. It can be the sound of very many things. It can be different things, even through the sensory, the infrared sensors. It can see many things. It can see buildings. It can see road signs that were not there yesterday. It can see, roadblocks that were not there yesterday. Roadblocks probably for people who are repairing the road, things like that. Yeah. So there are a continuous number of percepts that it will be receiving. It cannot be determined fully. They cannot be numbered, right? Known versus unknown. This is also known versus unknown is just like observable versus partially observable. So a known environment is, we can say that, known and unknown are not actually a feature of an environment, but is an agent's state of knowledge to perform an action. So a known environment is not really an environment. It is the state in which the agent knows what to do. If the agent does not know what to do, then we can say that it is working in an unknowable environment. So a known environment is one where the agent knows all the things that it's supposed to do. So that's why we are saying here, in a known environment, the results for all actions are known to the agent. It knows what to do, and it also knows the impact of everything it will do. But in an unknown environment, the agent needs to learn how it works in order to perform an action. It does not know until it knows, right? It does not know until it knows, meaning that it has to first perform an action, then learn from it. It does not know what is the impact of what I do. So I'll have to do it so that I can know the impact, right? So it's like you as a human being, you are trying out something new. You don't know how it is going to work out, but you're just trying, right? And then you will learn from it. learn from your experiences. So in unknown environments, agents learn from their experiences. But in known environments, agents work from knowledge. They already have a knowledge of actions they will perform and how the results of those actions, okay? Known versus unknown. Then accessible versus inaccessible. If an agent can obtain complete and accurate information about the environment, then such an environment is called an accessible environment. If an agent if an agent is not able to know, it's not able to access complete information about the environment, is an inaccessible environment. Again, accessible versus inaccessible can also be replicated as fully observable versus partially observable. Because in a fully observable, it can know its whole environment. In a partially observable, it can know only part of its environment. And then in a what? In accessible versus inaccessible, it can know by obtaining complete and accurate information about the state's environment, meaning it can know everything. But you see, sometimes it can be a partially observable environment. I want you to hear this. It can be a partially observable environment, but still accessible. How? Because if it has a model of how that environment works and it has complete and accurate information about everything in the environment, even if it cannot see its environment, all of it, but it has complete and accurate information about the environment, then it is a partially observable, accessible environment. Partially observable because it cannot see from all angles, it cannot see the whole environment, it cannot hear the whole environment, but it has complete information about that environment. Yeah. So that means it will not be caught unawares by different set of uncertainties. So a partially observable environment can be accessible, meaning that that agent has access to all the information it needs for that particular environment, even if it cannot see all of it. But an inaccessible is one that it doesn't have full information about. Therefore, it has to do what? It has to learn. It has to learn. If we are talking about an thermostat, an intelligent thermostat will be working in an environment which is accessible. Why would you say it's accessible? Because a thermostat works to either cool or heat a room. So basically to determine the temperature of the room to cool and heat it. So the environment is the room. The room, which is the environment, can either be cold or hot, or it can either be in this particular range of temperature or the other. So that environment is accessible because the temperature in that environment can be determined fully. All right, it can be determined fully. It's not trying to guess what the temperature will be. It is accessing the temperature as it is. So it has full and accurate information about the environment, the room. Therefore, we can say that thermostat works in an accessible environment. All right. But information, what we call, meteorological agents, like we can have intelligent weather or climate detectors, such things, or these climate detectors that normally are, they normally detect and are able to inform meteorologists of incoming storms, incoming tsunamis. Those kinds of intelligent devices and systems, they normally work in an inaccessible environment. Why? Because the earth is a dynamic. Also, the earth is a what? Is a dynamic environment. It keeps on changing, right? It keeps on changing. So meteorological weather and climate detectors and informers work on an inaccessible environment because Earth is a dynamic environment, and you cannot that meteorological device cannot access everything about the Earth because the Earth is huge, and also the climate is dynamic. It cannot have complete and accurate information about the Earth at a particular time because it keeps on changing. All right, so there we are. Those are the types of environments. I want to finish up by looking at the Turing Tests. And what is the Turing Test? We can have these. We can. Okay, let's finish up with the Turing Tests. Now, the Turing Test is a game that is used to test the intelligence of an agent. It was invented and modeled by Alan Turing, who is considered the father of artificial intelligence. So he came up with a game called the Turing Test. And the Turing Test, normally, the idea behind Turing Test is to measure the intelligence of an agent by comparing it with its human counterparts. By comparing it with its human counterparts. Okay, so basically, the Turing test checks whether a machine can think like a human or not. So in this test, Professor Turing proposed that the computer can be said to be intelligent if it can mimic human response under specific conditions, and the system can be deemed to be unintelligent if it cannot mimic human response under specific conditions. So the Turing test normally works, and I want you to look at this diagram here. The Turing test normally works with three entities. There are three entities that are involved in the game. Again, as I said, it's a game, but it's a game that is supposed to measure the intelligence of a system by comparing that system with its human counterpart. So the Turing test has three elements: the computer system itself, the human responder, and the interrogator. Now, how does it work? The game involves three players, as you can see here. The game involves three players: the computer, the human responder, and the interrogator. And the human interrogator is isolated from the other two players, and his or her job is to find that which player is machine among the two of them. All right, this is how it works. The interrogator is normally in a certain room and uses the system. Of course, he uses an interrogation system, which this human responder can see, and also this computer player can see or detect. So let's say it is a let's say it's a teacher, it's a robotic teacher, or a teaching assistant, a teaching assistant that's a system which is a teaching assistant. So this interrogator, what he or she will do through the interrogation system, he or she will ask questions to both, and these questions are equal. They are the same questions. So at the same time, he asks a question to the human responder, at the same time to the computer player. Of course, they go at the same time. Yeah. And then, for instance, a question like, because it's a teaching assistant, he should ask it like, define artificial intelligence. Now, this human responder here must be a teacher by profession. All right. And this one is a teaching assistant or a teacher, a teaching system, an artificially intelligent teacher. Okay. So, but this one is a human teacher who's a teacher by profession. That's why as I began, I said that this human respondent should be a counterpart. A counterpart meaning that they are well able to compete with the system. Okay. So this, when he asks that question, define artificial intelligence, because we want to see if this teacher is intelligent. All right. This particular teacher, this computer. because the one we are testing is the computer, the assistant, the teaching assistant. Okay, the one we are testing. We are not testing this one. This one we are just using them as a what we call, you know, do you know what you call patient zero, right? Or you know, it's like the moderator. Okay, we are using him to determine if he is intelligent. We are using this human professional teacher to determine if this system intelligent teacher is intelligent. So we ask this human interrogator, we'll ask a question, define artificial intelligence. And then this one will type in that interrogation system. Artificial intelligence is the science that involves building of systems that mimic human intelligence. And then at the same time, also this one will post an answer. That system will post an answer. Artificial intelligence is the ability of a system to mimic human intelligence. So this human interrogator checks whether these two answers correspond and whether they have key things that define artificial intelligence. So if this system has given an answer that corresponds well, even if it's not word to word, but it corresponds well and it matches with the answer given by the human correspondent, the human responder, then we say that this system, we conclude that this system is intelligent. But of course, we do not determine its intelligence by asking it one question. No, we ask it several questions. We ask it several questions, and then the interrogator can rate it. So it's the interrogator that asks, and also the interrogator that rates it. All right. So that is how the the Turing test works. The Turing test works. The Turing test works by basically putting two things into test: a system that is deemed intelligent, that has been programmed, and a human responder in the same field. So, for instance, if you are testing a robotic a robotic diagnosis doctor, yenye, the patient will be just feeding in what he feels and everything, and a biometric scan for the temperature. Yeah. Then this is a doctor. It's an intelligent doctor, or is deemed intelligent. But for you to test whether it is intelligent, you have to test it against a human doctor. All right. So that is the idea behind Turing test. The idea behind Turing test is to test the intelligence of a system by comparing that system with a human counterpart who is equally able. All right. So if it is a diagnosis system, it should be a doctor, right? Someone who is equally able. And then you will have an interrogator, and it is the interrogator that will be asking both the system and the human questions. And if the system is able to answer questions like the human, not exactly word to word, because that may not be possible, because they have not crammed, of course. Yeah, not exactly word to word, but there are key features that this one mentions that also the human counterpart mentions, then we will conclude by saying that the system is intelligent. Why? Because if it is able to mimic, the idea is to mimic. Can you see that word that I've highlighted there? If it is able to mimic human response, not exactly word to word, but key features of the human response, it is able to mimic, then we conclude that that system is intelligent. So that is the idea behind Turing test. All right. It works by having a system that is deemed intelligent, a human responder, and an interrogator. The interrogator is separated from this and this. So the three are all separated so that they cannot influence each other's answers. All right. So that they cannot influence each other's answers. Now, I will finish by saying this. There, of course, I can't remember the name of the movie, but of course, you know that these artificial intelligence concepts are normally featured in movies than in real life, right? But I can't remember the movie. But this person built a robot that has emotion, a robot that can feel things, a robot that is a human. Of course, the movie ends by showing the crisis of super intelligence, which we were talking about in the beginning of our unit, where, of course, it ends by the human turning against the builder, turning against the person who built it. But anyway, the idea is he did a Turing test of this machine, the robot that had the capabilities of a human, everything, feelings, humor, everything. It can work like a human. It can feel. It can have everything. It can feel things. So what it did, it put a human, a lady, because this robot was ladylike. It was a feminine robot. So it put a lady in one room and the robot in one room, and then him, the builder of the system, he was the interrogator. Okay, no, he was not the interrogator. He picked somebody. All right, a man. He picked a man, and then he put that man in another room. So each of these, the robot and the female person, the robot and the female person, the robot and the female person, they are able to see the man, but the robot and the female person are not able to see each other. You get that? So the robot can see the man, the human female can see the man. So the man is the interrogator. So the man will be asking this robot and also the human questions about love, about life, and therefore, as he asks the both questions, of course, he needs to see how they are responding. Then afterwards, this man is the one who should tell the builder of the system whether he found a discrepancy. Does he feel like one of the humans, or does he feel like the human or the robot is do you get what I'm saying? That does the man feel who is the human and who is the robot? In other words, the Turing test passes, the system passes, that system, whether it's a robot or a software system, it passes if the interrogator cannot tell which one is the human and which one is the system. You get the idea? So when the man, yeah, there's a movie called Jets. I think I need to look at that. As I was saying, the man cannot see the human female, and he also cannot see the robotic female. Yeye atakuwa kwa room, he will just be hearing. So if the man cannot tell which one is a robot, they all answer the same way, right? They all answer the same, or they have the feeling of a human. The way they answer, even the robot feels like a human. They can respond back like a human completely without behaving like a robot. You know, robots, what makes a robot is that input, output, right? And such things. So basically Turing test. So of course the resultant effect was he found out that he cannot actually tell between the robot and the human. And therefore the conclusion was that robot is intelligent. Sorry, I had gone, the system I just lost connectivity on my side, but I'm back. So what I was saying about Turing test is that if the observer cannot tell, if the observer or the interrogator, not the observer, if the interrogator cannot tell who is the human and who is the system, then we can say that that system has passed the test. All right? Yeah, so that's how Turing test works. You test a system by comparing it with a human and the interrogator. So the interrogator should not be the person that built it. You know why? Because the person who built it might be able to know the questions to ask, to trick the robot or to trick the human. Okay? So if the interrogator is normally somebody, an outsider, somebody picked. Okay? So the interrogator can be, for instance, if you as the IT person, you had been employed to be in a team that builds an intelligent diagnosis system, and you've already built it. So you want to test it whether it is intelligent like a human doctor. So you will bring in a doctor who is a doctor, all right, a doctor by profession, and then you will bring an interrogator who is not a doctor, right? Who is just someone, right? If a patient, for this sake, because the person will be asking it is a patient, so you'll bring in a possible person, just a person who can be a patient, and you bring a person, and that person will be asking it questions like, I am having, uh, I'm experiencing, headaches. I'm experiencing frequent stomach aches and such things. And I ask questions, and then he waits for answers, and then he hears what each says, and then at last they are actually told, by the way, answers B or response B came from this part, and response A came from this part. And then they are told, could you tell if one was a robot talking to you and another was a human? Then if they say, actually, I could not notice, they were all giving me very accurate answers, they could talk back to me just like a human, I could not notice. Then you can now clap for the system and say that system is intelligent. You get the idea of Turing test. So that's how Turing test works. So, well, we come to the end of our class. Okay. Hope that you have gotten something. Right. So, is there any question before the class ends? So, of course, you can look at some of these movies that have impression of these things, right? So you can get what actually happens. There is also, let me check here. Let me check. There's one that, let me check here. There is a 2020 series called Upload. You can look at Upload. The reason I recommend these movies and series because they give the concept, right? They show the concept of artificial intelligence. So they are not only for entertainment, but they are able to tell you how people outside who are interested in artificial intelligence view artificial intelligence. So there is a series called Upload, but it's just one, just one season. The series called Upload, so you can look at it. So Upload is a very interesting system. A very interesting series. The whole series about artificial intelligence. So you can look at it. I think 2013 you looked at a series called Person of Interest. There was a series called Person of Interest. It also featured artificial intelligence, person of interest. Uh, there was also a movie called Passenger. It also featured artificial intelligence. So basically, when you look at these movies and these things, especially for this century, they normally have this concept of artificial intelligence, which tells you what? It tells you that people are interested in these things, and that means that in the next years, artificial intelligence is going to be the rule rather than the exception. Right now, it feels like it's more of the exception rather than the rule, but it's going to be the rule rather than the exception because people are thinking about these things largely. Largely. So, well, then we come to the end of our class. Come to the end of the class. If there is anything else that I need to inform you, I'm going to inform you via WhatsApp so that you can know. So then have yourself a good day. I'm going to end the session. Westworld. All right. Thank you. Yeah, have a good day too. So keep learning, go to YouTube, find things that you can learn experientially. You look at those things, and you also find articles that you can read and such things. I think artificial intelligence is one of the most interesting areas today, apart from programming itself. So keep learning, keep looking at those things so that you can acquaint yourself with knowledge. All right, have a good day. We'll meet next time.